Hello, am I audible? Hello.
Yes, ma'am.
Oh, okay, good afternoon, everyone. I welcome you to the fourth problem solving session of graph theory. So, I hope I hope I'm audible and my screen is visible to you.
Yes, ma'am.
Okay, so we'll start. So in the week four, so today we'll be discussing matching in graphs and in particular in bipartite graph. So in the last week we have learned about simple graphs and we have also introduced the bipartite graph. Now we'll be looking at this concept of matching. So first of all, what let's recall what is a matching. So matching is basically it is a set of edges. Given a simple graph G, matching is a set of edges of that graph such that every vertex of graph G is adjacent to at most one edge in that matching set. So each edge in that in each vertex in each vertex in a matching is allowed to be adjacent to at most one edge. So in this so suppose this is the bipartite graph that has been given. This is the bipartite graph. So here we can see the edges which are colored with blue and edges which are colored with red, they form two different matchings, because in each of so if we take M, so we see each no vertex is attached to two edges. So we see that M and M dash are matching. So this is what a matching is. Now the problem is, we are interested in finding the maximal matching in a graph. So before that, let's see what is an alternating path. By an alternating path, I mean a path which is alternating between matched and unmatched edges. So a path is basically you go from one vertex to another, but if so alternating path is defined with respect to some fixed matching. So for it has to alternate between matched and unmatched edges. So if you start with a matched edge, then you go to unmatched edge, and so on. And augmenting path is a special type of alternating path which start and end with unmatched vertices. So it is saying that augmenting path should start and end with unmatched vertices. So please note that we meant unmatched vertices. So it's not that so if you have an alternating path which is starting with a unmatched which is starting and ending with unmatched edge, but it is not starting with unmatched vertices, then that path won't be an augmenting path. So it is necessary for an augmenting path to start and end with an unmatched vertex. So it starts with an unmatched vertex, end with an unmatched vertex, and in between all the edges are alternating between matched and unmatched edges. So for example, in this above graph only, if we fix our matching M, so we see if we want to find an alternating path, so we are looking for a path which is alternating between matched and unmatched edges. So you can see this path WAU is an alternating path, and it is an alternating path with respect to both M and M prime, because WA, this edge is in M and this edge is in M prime. And so if why it is an alternating path with respect to M, because WA is a matched edge with respect to M and AU is an unmatched edge with respect to M. So it is an alternating path with respect to M, and in similar fashion it is also an alternating path with respect to M prime. But note these are not augmenting paths. Because for augmenting path one is required that it should start and end with an it should start and end with a unmatched vertex. So in this example, if we want to construct an augmenting path with respect to M prime, so M prime, these are the two red edges. So we want to, if we want to construct an augmenting path with respect to m prime, what we have to do, we have to start with some unmatched vertex. So in this m prime, in m prime, the matched edges are a, w, c, v. And what are the matched vertices? Matched vertices are a, w, c, v. So you have to start from a vertex. You have to start from a vertex other than these four vertices. So what are the vertices that are left? Okay, so this is a augmenting path with respect to m, first one, and this is so see, so if we want to construct a augmenting path with respect to m prime, so these are the matched vertices a, w, c, v. So we have to start with a vertex which is not matched. So what are the leftover vertices? A, w, c, v. So either we have to start from b or either we have to start from u. So let's start from u. So we see u, a, w, and w, b. This will be an augmenting path with respect to m prime, because of the same reasoning. And similarly, wb, bv, and vc, this will be an augmenting path with respect to m. So now why we are interested in matching and augmenting path? So we see that matching and maximal matching and augmenting path have a very nice relation. So we have this result that a matching m is maximum if and only if there are no augmenting paths with respect to m. So if we want to find if we are given a matching, and if we can find an augmenting path with respect to that matching, we can surely say that that matching is not a maximal matching. So, and using and there is also an algorithm to calculate maximal matching using the augmenting paths. So let's work out that algorithm first. Let's try a question on that algorithm. So first question is that using augmenting path algorithm, we have to find maximal matching. So what is the we have seen in the result in the class that matching is maximum if and only if there are no augmenting paths with respect to m. So now we want to find a maximal matching using these augmenting paths. So what is the algorithm? First of all, we start with m equal to empty. So m is basically the set of matched edges, and we are setting m to be empty, and whenever while there is an augmenting path with respect to m, we'll take that path p and we look at the symmetric difference of m and p. By symmetric difference of m and p, we mean that we take the union of m and p and remove those edges which are present in both m and p. So that will give us the symmetric difference, and the new m will be this. So this is the algorithm. Now let's try to find the maximal matching. So we want to find the maximal matching for this using the algorithm. Yeah, using the augmenting path algorithm. So I am writing down m, and then the augmenting path, and then the new m. So first we have to start with an empty set. So can you give me an augmenting path with respect to empty set? Can anyone give a augmenting path with respect to empty set? So in this question we are trying to find maximal matching using augmenting path algorithm. So we have to first we have to give a augmenting path with respect to a matching set. With respect to matching. Now what is an augmenting path? Augmenting path, it is an alternating path which should start and end with unmatched edges. And since your m is empty, there are no edges which are matched. So any edge will be an augmenting path with respect to m. with respect to empty set. So for first I start with the I take my augmenting part to be AV, and now if we look at the symmetric difference of M and P, it will be just AV. So my new M is AV. So now this is my new M. So now my new matching is comprising of AV, just one edge. Now can you give me an augmenting path with respect to M? Anyone? So does everyone understand what is an augmenting path?
Can you explain once again, ma'am?
Okay.
Augmented.
Augmenting path. Yes. I'll explain once again. So so first of all I defined what is a matching. Matching is basically set of edges, and each vertex should be adjacent to at most one edge in the set. So if I take my M to be AU AV, this is not a matching because this vertex A is attached to two of the edges. So this is not a matching. So for matching we need that all vertices should be attached to at most one edge. Now once we know what a matching is, we fix a matching and we define an alternating path with respect to a matching. By alternating path we mean that it should be a path which is alternating between matched and unmatched edges. Basically, you are constructing a path in which first edge is matched, other edge is unmatched, second edge is unmatched, third edge is matched, fourth edge is unmatched. In that alternating in that manner, or it can either start with matched edge or unmatched edge. So if in this example, if I take my M to be AUBV, the edges which are colored with blue, and if I want to construct an alternating path, so you can see that UA is a matched edge. Now the other edge that I have to choose is the unmatched edge. So we see that AV, it is not colored blue, so it is not a matched edge in M. So next edge is AV. And VB, if I take VB, it is matched with respect to B. So first edge is matched, second edge is unmatched, and third edge is matched. So this is an alternating path because it is alternating between matched and unmatched edges. And now what is an augmenting path? Augmenting path is an alternating path. So first of all, it has two conditions. First of all, it should be an alternating path, and secondly, it should start and end with unmatched vertices. By unmatched vertices, we mean that all those vertices which are not present in the matching. So now, if my M is AUBV and if I want to construct an alternating path, augmenting path. So what do I do? First of all, first of all, this augmenting path should start with an unmatched vertex in M. So in M, A, U and B, V are the matched vertices. So if I want to construct an augmenting path, it should either start with C or W, and it should end also with C and W. So suppose I am starting it with C. So it is starting with C. Suppose CV is the first edge. Now CV is an unmatched edge with respect to M. So now it has to be an alternating path. So second edge should be a matched edge. So we see that VB is a matched edge. So we can take VB to be the next. Now this is a matched edge. This is a matched edge. But now to construct an augmenting path, we should also end with an unmatched vertex. So you see that this is not an augmenting path, and we can't yet. So we'll have to add an unmatched edge. So if we add BW, CV, VB and BW, this is an augmenting path with respect to M, because CV and BW are unmatched edges, C and W are unmatched vertices, and it is an alternating path. So now you understand what is an augmenting path? Is it clear?
Yes, ma'am.
Okay.
Got.
Now if augmenting path is clear, so now what we are trying to do is we are trying to so we have this augmenting path algorithm to find maximal matching. So what is this algorithm saying? First we start with an empty set, then we look at the augmenting path with respect to m. So since m is empty, there are no matched edges. So we have to all the vertices are unmatched. So we can take any any edge. So if we take AV, suppose AV, so A and V are both unmatched with respect to empty set, and plus it is an unmatched edge. So it is satisfying all the conditions for an augmenting path. So therefore we see that AV is an augmenting path. And once we have got an augmenting path, we take the symmetric difference of M and P. And symmetric difference of M and P is basically M union P minus M intersection P, and which is just AV. So now the new matching set that we have is just the single edge AV. Now can you give me an augmenting path with respect to this matching which has single edge AV? So if it is first of all, augmenting path should start with a unmatched vertex. So you have to start it with some vertex other than A and V.
BW, ma'am.
Yeah, BW, okay. BW, okay. So if we take BW, yes. So do you want to, are you taking just BW or do you want another? So is BW the path that you are giving?
Yes, ma'am. Next, we can give DX.
Okay. Okay. First of all, okay. So first of all, we are taking AB and BW. So now this is an augmenting path because it is starting with an unmatched vertex and ending with an unmatched vertex. So we see that this is and now the new matching is the union and intersection AB BW. Okay. Now we have a new matching AB and BW. Now, with respect to this matching, can you give me an augmenting path?
Yes, ma'am. Next, DX, ma'am.
Okay, okay, yes, we can take dx, and this is the new matching. Okay, AB, BW, and dx. Now, the new matching is this. Now, can you give me another can you give me an augmenting path with respect to AB, BW, dx? So, this is our matching up till now. AB, BW, and dx. Now, now we have to give a augmenting path with respect to this. So you see, an augmenting path should start and end with an unmatched vertex. So these are the vertices which are colored as red are the matched vertices. Now, if we have to give an augmenting path, it should start from the rest of the vertices which are not circled. And an augmenting path, uh, so it should start with either C, Y, U, sorry, E, Y, U or C. And this, what is the second condition? So you see, so what was he doing? So if we have to give an augmenting path, it should start and end with an unmatched vertex. So if among the unmatched vertices we have an edge, then we can give that as our augmenting path, because so but now we see the leftover vertices are CU and EY. So there are no edges between CU and EY. So we can't give a path which is comprising of just one edge. But can we give some other path? Can we construct some other augmenting path? So suppose, so we know that if there is some path, if there is some augmenting path, it should start with either C, U, E, Y. Suppose it starts with Y. For timing, let's say it starts with Y. So Now if it is starting with y, it is and y d is the only edge possible. Now this is an unmatched edge. Now we have to give an alternating path, so we should take some matched edge. So the dx is the only possibility. But now we have to give a unmatched edge starting with x. So we see that there is no unmatched edge starting with x, and x is already a matched vertex. So this is the only alternating path. This is the only alternating path that is possible from y. Is that correct?
Yes, ma'am. Yes, ma'am.
So we see that if this is the only, but is this an augmenting path? Is y d dx an augmenting path with respect to this matching?
No.
No, ma'am. No.
No. Why?
There is a common vertex D.
So it should start and end with non-match.
Yes. Yes. So yeah, it should start and end with a non-match vertex. But x is a vertex which is already matched. So this cannot be an augmenting path. Okay. So somebody said that it has a common vertex. So see, we are when we are constructing so in a matching is not allowed to have common vertex, but when we are constructing path will already, because it is a path, it will have a common vertex. So having a common vertex is not an issue. So whoever said that it has a common vertex, is it clear why it is not an why it is not a unmatched, why it is not an augmenting path?
Yes, ma'am. Yes, ma'am.
Okay, so we see that there is no augmenting path starting from y. So can you, so now the next option is C. So can you find an augmenting path starting from C? So if we are trying to find an augmenting path starting from C, so first of all we have two possibility. Either we take the edge CV or we take the edge CW. So these are the two possibilities. Suppose I am taking the edge CV. Now this is an unmatched edge.
CV is the only possibility, no?
Sorry,
As we can. CV is the only possibility. No, CW. Okay,
CW.
okay.
Oh, sorry, I meant E. This is E. Sorry, I meant E. EV and EW. This is so first second E. Now if we start with E, EV and EW are the only possibility, right? Now if I am taking EV, so EV is an unmatched edge. Next edge should be matched. So suppose it is the only matched edge
VA.
VA. And see, we are getting in the same problem. Now we want to have a unmatched edge, but there is no okay, there is an unmatched edge which is AW.
AW.
There is an unmatched edge which is AW. But now, and there is a matched edge WB.
HWB.
Yeah. But now, once we are ending at B, we don't have any other edge going out of B. So is this an augmenting path? EVVAAWWB?
No.
No. Why? Because of the
Because it,
yeah. Because of the same reason. Because B is the vertex which is already matched. So we see that we don't have, this is also not a case. And similarly, you can see for all the four vertices, we won't be able, like if we look at all the if we look at all the possibility, we won't be able to find an augmenting path. So if we are not able to find an augmenting path, this algorithm stops, and therefore we claim that this is the maximal matching. AV, PW and DX is the maximal matching. Is this clear? Is the question one clear to everyone?
yes, no.
Yes, ma'am.
Okay. So if it is clear, let's move on to next thing. Now, once we know how to find maximal matching, now there is also a call. Now we want to know when the perfect matching exists. So in the class we did some theorem on matching in bipartite graph. So first
Ma'am,
there, yeah.
I have one doubt, ma'am.
Yes, yes.
In that symmetric difference formula, we are not getting any intersection between the matching and the um,
Yeah.
path, augmenting path.
Yes.
Likewise,
Hmm.
when will we get that intersection, ma'am, between the matching and that path, augmenting path?
Okay, yeah. So see, okay. So this was one of the method. This was one of the way to get the augmenting path. So instead of here, instead of BW, we could have constructed. So we if we could have constructed now if our matching was AV, we could have constructed some other thing also, right? Like maybe wait. Uh, so this is AV. So yeah, if we have construct now if we are matching was AV, M was AV, and we look at this path, say CV, VA, and AW. So is this path an augmenting path with respect to this matching? With respect to matching AV?
Yes, ma'am.
Yes. So now we see that they have a common edge, common. So instead of BW, if we have chosen this path, now they have a common edge AV. So now the new M will be the symmetric difference. So what will be the symmetric difference of M and P? It will be CV and AW. Because what is the symmetric difference? This is M union P minus M intersection P. So CVAW. So in this case, so if instead of BW, if we had chosen this path, we would have been getting this as a new M. So was this your question?
Okay, ma'am. Yes, ma'am. Clear,
Like
ma'am.
what was your question? Like you wanted to.
Um, Ma'am, I have asked whether the matching and the augmenting path have intersection in all the problems, or whether they don't exist in some other cases.
Sorry. Can you repeat your question? Hmm.
Ma'am, whether the intersection between the matching and the augmenting path always exists, or otherwise, is there any case for its non-existence?
So it can, so see now here in this example only, this was so with respect to this matching AV, we are getting two path. One path is BW, which is an augmenting path. Other path is this path CV, VA, AW. So in this, so you see, so this particular augmenting path has no intersection, but this particular augmenting path has an intersection. So so if you are given a matching, if you are given a matching, both possibilities are possible, that you can find an augmenting path with an intersection, and you can find an augmenting path with a, or like so it's not that you'll be always able to find an augmenting path without some intersection.
Okay, ma'am. Okay, ma'am.
Okay, is it fine?
Yes, ma'am. But
Yeah.
only one doubt, ma'am. I have here. I want to know which intersection you are subtracting from that union, ma'am.
So see,
So
so this is my M is AV and P is CVVAAW. So if I take M union P, it will be AV, CV and AW. If I take M intersection P, this is CV. Oh, sorry, AV. So my symmetric difference is AV, oh sorry, CV and AW. So I am subtracting this edge AV from the union because it is present in both the cases.
yes, ma'am. Yes, ma'am. Now it's clear, ma'am. Thank you. Thank you.
Okay, yeah. So see, there are two definitions of symmetric difference. Maybe that's why you're getting confused. So if we have A, B, so symmetric difference is this shaded portion. So you can see that symmetric difference is either, you can write it as A minus B union B minus A. This portion is A minus B, because we are in this from this set A, we are subtracting the part which is contributing by B, and this portion, this other portion is B minus A. But this is the symmetric difference. But you can also see that this is nothing but equal to, you take A union B, and from the union you subtract this portion. So these are two equivalent definition of symmetric difference.
Yes, ma'am. Thank you. Thank you. Clear, ma'am.
Okay. Now to find matching in, now we have some theorems which guarantee the existence of matching. So first of all, we have this Hall's theorem. So Hall's theorem says, so Hall's theorem is for a bipartite graph. Suppose G is a bipartite graph and X and Y are the bipartition, then G has a matching that saturates X if and only if for every subset of X, the order of S is less than equal to the order of neighbors of S. So first of all, what do we mean by G has a matching that saturates X? That means we are able to find a matching M, that is a set of edges which all the vertices of X are present in some in one of the edge. So that is what we mean by G has a matching that saturates X. And what is the if and only if condition for Hall's necessary and sufficient condition for a bipartite graph to have a matching that saturate S is that if we have any subset S, then the number of elements in S should be less than equal to the number of neighbors of S. So what do we mean by neighbors of S? So let's I have this example. This is A, so all these, so these are vertices A, B, C, D, E, F, G, H, and X is the first set. So now, okay, maybe this is, so now if I have S is if I am taking my S to be AD. So what is NS? Can anybody tell? If S is AD, what is NS? NS is the, we are taking all the neighbors of AD.
AE and DE.
What? Uh, A. So what are the neighbors of AD? So first of all, what are the neighbors of A?
EF.
E, F. Yes. And what are the neighbors of D? G, H. So we see that these are the neighbors.
You can't take
E and H, ma'am, for D.
E, G, and
E, G and H, ma'am, for D.
Yes, E, G, H for D. But E, we have already included E, so E, F, G, H are the neighbors of S. Is it fine? So for S, neighbors of S are E, F, G, H. Is this fine? So is it fine within? So now if we take S to be A and C, what are the neighbors of S?
E, F only.
E, F. Anything else? No. So we see neighbors of AS is EF. So now we know what do we mean by neighbor of S. And Hall's theorem give us a necessary and sufficient condition. For existence of matching that is saturating X. So from Hall's theorem, can you conclude if this graph has a matching that saturates X? What do you think? So first I consider S1 as AD. So we see that for this S1 this condition is satisfied. So S1 has two elements, but S1 has two elements and neighbors of S1 are 4. So this condition is satisfied for S1. And if I take my S2 as AC, and then the neighbors were coming out to be EF. So for S2 also this condition is satisfied. But we want this condition to be satisfied for each subset of S.
Means saturates means what? Can you explain?
Saturates mean
Matching X.
so the matching, so we have this matching which has some set of edges E1 ek. Saturates X means that each vertex of X should be present in one of the edges,
Got.
one of the edges
Okay.
of M. So
Okay.
so So Hall's theorem is saying that if we have a bipartite graph, then G will have a matching that saturate X. That means G will have a matching which is containing all the vertices of X if and only if for every subset of X the order of S is less than equal to the order of neighbors of S. So this is the necessary and sufficient condition. So if we want to show that this graph does not have a matching that saturate X, we want to find a set, we want to find a subset S3 of X such that this condition is not true. That is, order of S is strictly greater than order of NS. So can you find some subset of X which has fewer neighbors than S?
ABC.
Okay, good. So if why? So if we take S3 as ABC, then neighbors of S3 will be
EF.
EF, right? And we see that this is strictly less than it is strictly greater than order of NS3. So by Hall's theorem, we cannot have a matching that saturate X. And also it is clear, this one way condition is always clear that, so see, this so we can either apply Hall's theorem or we can even directly see. So suppose we have a matching that saturate X. That means that matching should have an edge coming out from A, B and C. But since A, B, C just have two neighbors, there is no way possible that we can find three edges. We can find three edges going from A, B, C which have no common vertices. So if we'll be picking three edges from ABC, so we'll see since E and F are the only neighbor, we won't be able to do that, and that's why this is seeing that this condition is necessary is easy. So if we want to, so is it clear why this graph does not have a matching that saturates X? Is it clear for everybody?
Ma'am, that saturation is still in doubt, ma'am. Please explain it once again.
Okay, so by saturate, okay, you mean what do we mean by saturation?
Yes, ma'am. Saturates X.
Saturates X. So see, X is the first bipartition A B C D. X is the first bipartition A B C D. So G has a matching that saturates X means that we want saturate X. So what is a matching? Matching is basically it is some collection of edges such that each vertex is adjacent to at most one edge. Now a matching that saturates X means that a matching that consists of all the vertices of X. So replace saturation by matching consisting of all vertices of X. So is this line clear? What do we mean by this thing? That matching consisting of all vertices of X.
Yes, ma'am. Yes, ma'am.
So
Okay.
So you can so matching that saturates X means just this, that matching which is consisting of all vertices of X.
Yes, ma'am. Here D is missing, so it's not saturates.
Yes. So yeah. So if you
Okay.
see that, now if you want to find some maximal matching of this graph, so see if we choose AE first and if we choose BF the next one, there is no edge left for C. So C is connected to F, but we cannot choose CF for a matching because BF is already chosen, and then DG.
Yes.
So you see that if we pick up any matching in this graph, it will miss at least one vertex of X. So this graph cannot have a matching which is consisting of all vertices of X.
Yes, ma'am. Yes, ma'am. Understood, ma'am.
Okay. So and this is this is what so understanding what is saturation is fine. Now does everyone understood the statement of Hall's theorem also?
Yes, ma'am. Got.
Okay.
Yes, ma'am. Got it, ma'am.
Okay. Now 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 second thing is, so after Hall's theorem we have Koenig's theorem. So what is Koenig's theorem saying? So before stating Koenig's theorem, I want to introduce another definition, which is definition of a vertex cover. So what is a vertex cover? Vertex cover is basically a subset of vertices, and now it is a subset of vertices and all the edges. It is a special set of vertices such that all the edges which are present in graph should have at least one vertex from that set S. So a vertex cover is a set S of vertices of G such that every edge in G is incident to some vertex in S. Okay. So in this above graph, so if vertex meaning of vertex cover is clear, so in this above graph, can you give me a vertex cover? So first of all, you see that set of all vertices will always form a vertex cover. Is it clear why set of all vertices will always form a vertex cover? So in this above graph, if I take my V to be the whole set of vertices A, B, C, D, E, F, G, H, this will form a vertex cover. So from by definition, is it clear why this is a vertex cover?
Yes, ma'am. Because any edge will be incident with that vertex.
Any edge will
So
be,
we
yeah,
incident with that vertex, and we have all vertices in that set.
yes,
So it will be a vertex cover.
yes. Okay, good. So we see that a set of all vertices is always a vertex cover. But in this graph, can you give me a smaller vertex cover? So basically, you want to give me some set of vertices. So some set of vertices such that every edge has at least one end one end at least one end sorry at least one end point of every edge is should be present in that set. So okay, let's see this. Suppose I take my V prime to A, B, C, D, which is just X. Is it an vertex cover? Is V prime, which is A, B, C, D, V prime, if I take my V to be X, is X a vertex cover?
Yes, ma'am. Yes.
Yes. So in a bipartite graph, you can always say we can always see in a bipartite graph the bipartition set X and Y, they will always form a vertex cover because all the edges in a bipartite graph have at least one endpoint in X. Because in a bipartite graph, edges are going whose edges have one endpoint in X and one endpoint in Y. Therefore, X and Y both will form a vertex cover. Now, now can you give me a vertex cover which is a subset of Y. Or no, sorry, not Y, any vertex. Now give now any, so is there any vertex cover other than V, X and Y? So we have found three vertex cover, V, X and Y. Is there any other? So suppose, so see, in this only EFGH is a vertex cover. Now can we find a subset of this, some, can we remove some vertex from this set such that it remains a vertex cover?
Can we take D, F,
D, yes, say D,
D, F,
hmm,
and
D, F,
D and F also?
D, E and F.
Yeah, D, E, F.
So yeah, so see, yeah, so this vertex cover had four, this vertex cover has four vertices. Now this is a smaller vertex cover, DFE. So first of all, is it a vertex cover? So to show that it is a vertex cover, every edge every edge should be incident to one of the vertices here. So now we see that EF is a vertex. All the edges going from ABC are connected to EF, and all the edges going from GH are connected to D. So we see that if we consider any edge in this graph, one, at least one end point will be DF or E. Therefore DFE is a vertex cover of this. And this should not be surprising also, because by Konig's theorem says that in a bipartite graph G, size of minimum vertex cover equals the size of maximal matching. So in this graph we were able to find, found out that maximal matching has size 3. So by this theorem we should be able to find a vertex cover which has just 3 vertices and
This,
submit,
ma'am,
and
if we take only D and F, it does not become vertex cover.
yes, okay. Yeah, if we take just DF, it won't be a vertex cover. Yes. Yeah. So yes, it won't be a vertex cover. Think why it won't be a vertex cover. You just have to look, to show that it is not a vertex cover, you just have to pick a edge in this graph G which whose endpoint is neither D nor F.
Okay, okay.
So
B is,
if you take this
yeah,
edge BEAE,
yeah.
so see, these won't have any, these won't have edges though. So the DF is not a vertex cover.
Got,
And
got.
Konig's theorem, so Konig's theorem is saying that in a bipartite graph G, size of minimum vertex cover equals the size of maximum matching. And we have found out that maximum matching has size 3. And we have also found a vertex cover of size 3. So by Konig's theorem, we cannot have a vertex cover which has just 2 vertices. And we are also seeing that also. So if you pick any 2 vertices from this graph, those vertices won't form a vertex cover. So is this clear? The statement of Hall's theorem and Konig's theorem clear to everybody?
Yes.
Yes, ma'am.
Okay. Okay. Okay, we'll do some questions first and then we'll come to this. Okay, so now the second question is that suppose M is a maximum matching of graph G. Which of these form a vertex cover of G? So both of them can form a vertex. So first part is this. So first question, so you are given that M is a matching, M is a maximum matching. Suppose M is a maximum matching. So I'm saying that M is E1, EK, and these are the vertices V1, uh, V1 W1 and VK WK. So M is a maximal matching. So do you think that if we take all the vertices in M, will they form a vertex cover? So the answer for A is yes. I am saying this. So vertices in M, vertices of maximum matching, form a vertex cover. But now we want to prove this. So first of all, let's look at some examples. So in the previous example only, in this previous example only, in this previous example, this was our maximum matching. So wait, let me go. What is happening? Okay, sorry. Why it is happening this? Okay, sorry. My this is hanging. What is happening? Yeah. So okay. Okay, wait. Yes. Yes. So okay. Uh, yes. So is the screen visible? Okay. Hello. Yes.
Yes, ma'am.
Yeah. Okay. So sorry, like something happened. Okay. Yeah. So now the first question is, we want to show that vertices of maximum matching form a vertex cover. So in this was our previous example. So this was the maximum matching that we were getting. So maximum matching was basic in this maximal matching was AE, BF and DG. And the vertices of and the vertices in this matching are A, E, B, F, D, G. What do you think? Does this set of vertex form a vertex cover for this? So does V form a vertex cover of this graph?
Yes, ma'am. Yes, it covers all every edges.
Yes. So in this particular example, we can see this. So now if we want to prove this, that vertices of maximum matching form a vertex cover. So what do we have to do basically? We have to basically show that, so vertices of maximum matching form a vertex cover. So basically we have to show that if we pick any edge, if we pick any edge, so so this is the if we pick any edge from vertices outside matching. So basically, so we have to show that this vertices of maximum matching form a vertex cover. So we have to show that any so any so if this is the vertices of M, vertices of G minus vertices of M. So if we pick any vertex X which is not present in the matching, suppose X is a vertex not in matching, and suppose XY is an edge. So first of all, since X is a vertex not in matching and XY is an edge, so this edge cannot be in, this edge is not a matched edge. So but is it possible that this Y does not belong to the matching set? So if we want to show that vertices of maximum matching form a vertex cover, we want to show that, so if we can pick up any vertex which is lying outside the matching, so this is our graph G. These are some matched vertices. This is the set of matched vertices, and this is the complement, unmatched vertices. This is matched vertices, and we have some maximal matching happening here. Okay, so this is the matching graph, and we have some other vertices lying in this. Now we are claiming that these vertices which are matched, they are forming these vertices which are matched, they are forming a vertex cover. So to show that it is a vertex cover, we have to basically show that if we pick any edge, other than this matching edge, that if we pick any edge from this, so any edge from the unmatched vertex should go to a matched vertex. To show that this is a vertex cover, we have to show that every edge should have at least one matched vertex. If we can show that every edge of G has at least one matched vertices, then we are done. Is it clear that why we are done? That if we want to show that vertices of maximum matching form a vertex cover, it is sufficient to show that any edge of G has at least one matched vertex, because that is the definition of vertex cover. We want to show that matched vertices form a vertex cover. So we want to show that any edge, if we pick any edge in graph G, it should have at least one matched vertex. Right? Is it clear?
Yes, ma'am.
So now suppose not. Suppose we have an edge E. So we have an edge E, which has both the vertices are unmatched. So this is the case. Suppose we have an edge between two unmatched vertices. Is it possible? So
No,
we
ma'am,
know
no.
that this is a maximum matching. So can we have an edge between two unmatched vertices?
No, ma'am.
Why?
Ma'am, as per the definition already you said, yeah, the edge each edge should have one matched and one unmatched vertices, ma'am.
This
So
we
here, so
this we want to show. We want to show that every edge has at least one matched and one. So we are given that this is the maximal matching. This matching is maximum, and we
yes,
want
ma'am.
to show that matched vertices form a vertex cover. So we want to show that any edge has at least one matched vertex. So now we want to prove it by contradiction. Suppose we have an edge which has both the vertices which are unmatched. Is it possible?
Ma'am, that's not possible, ma'am.
Why?
Because
Yeah.
in this diagram itself, you can see, ma'am,
Yes.
the edges E and F and CF and DH
Hmm. CF and
have
DH. Yeah.
Yes, ma'am. They are having one matched vertex there, but no edges between unmatched vertices are given, ma'am.
Yes, yes. In this particular example, it is true that we have no unmatched vert. So here the matched vertices are A, B, E, F, and D, G. Yes, you are right. So here the matched vertices are this, and unmatched vertices are C, H, and there is no H between unmatched vertices. So
Yes,
we
ma'am.
want
Yes,
to show,
ma'am.
so this is happening for this particular example, but we want to prove that this will happen in all maximal matching. So if we have a bipartite graph, and if we take a maximum matching from that graph, if we have a graph and if we take the maximum matching from that graph, and if we consider all the matched vertices, there cannot be a edge between there cannot be a edge between two unmatched vertices. So can you think of a reason why it is not possible? We are
Because
given.
if we draw that H, no CH, ma'am, in this example, it will become a matching only.
Yes, yes, that's the point. Good, good. So if we have a, if we, very good. So if we have a unmatched, if we have a edge between unmatched vertex, if we have a edge between unmatched vertex, then this edge can be added to the matching. But we have already shown that this is a maximal matching. So we cannot have any edge between unmatched vertices, because if we have any edge between unmatched vertices, it will contribute to some matching, and we will be able to construct a bigger matching. But we already know that the matching that we are given is the biggest. So now is it clear why the
Yes.
vertices of maximum matching form a vertex cover?
Yes, ma'am. Clear, ma'am. Clear.
Is it clear for to everybody?
Yes, ma'am, clear.
Okay. Yeah. So now this one was this. So we saw that if we have a maximum matching in graph G, then if we take all the vertices in M, then this form a vertex cover. Now we want, now the second part is, what if we pick one vertex from each edge in M? We pick up our favorite vertex from one edge in, will that form a matching? What do you think? Will that form a vertex cover? So what, now the second question is, we are given some maximum matching. Suppose in this case this is the maximum matching, and what is the vertex set we are considering? We are picking one vertex from each of the edge, not just one vertex from each of the edge, and then we are asking, will that vertex set form a will that vertex set form a will that vertex set always form a vertex cover? So what do you think? So see, so we have these three edges, A, E, B, F, D, G. So suppose I, from A, E I pick E, from B, F I pick F, and from D, G I pick G. So I see that this E, F, G, we already E, F, G. Yes. So if I pick A, E, B, F, and E, G. So is this forming a vertex cover? Is it E, F, G forming a vertex cover for this graph?
No,
No.
E, F, G.
Yes.
No,
Why?
H will be.
DH edge is not covered by these vertices, right?
Yes, ma'am. Yes, ma'am.
So so for B it is false. So for A it was yes, and for B we have seen that it is not always true. But see, like, yeah. So this is the, so if we have a maximum matching, the vertices of maximum matching form a vertex cover. But if we just pick one vertex from each of the edge, then it might or might not form a vertex cover. So is this question clear?
Ma'am, in
Yes.
A option, you have proved that the vertices of a maximum matching form a vertex cover.
Yes, yes.
But in the question, it was given only vertices in Oh, that's matching. Okay, 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 ma'am. Thank you, thank you.
Yeah.
Correct.
Okay. Okay. Is it clear for everybody? Is it clear to everybody this question? Okay. So okay, so next question is this, but I think this is done in the lecture, so we'll we'll look at the fourth one. Yeah. Yes. Now now we are given that the next question is that we have a G is a bipartite graph on n vertices. Now we have to show that size of maximum matching is greater than equal to total number of edges divided by delta. Here delta is the maximum degree. So let's do this. Let's prove the A part. So first of all, G is a bipartite graph. G is a bipartite graph. So by Koenig's theorem, what is the size of maximal matching equal to? By Koenig's theorem. So we have seen that in a bipartite graph, by Koenig's theorem, size of maximal matching is equal to size of minimum vertex cover, right? This is Koenig's theorem. So now we want to use Koenig's theorem to prove this inequality. Size of minimum vertex cover. So let's do this. So suppose Q equal to V1 Vk is the suppose Q equal to V1 Vk is the minimum vertex cover. Is the minimum vertex cover. Now if this V1 Vk is the minimum vertex cover, so now we are given that delta is the maximum degree of vertex. So can you give me number of edges? So what is the maximum number of edges adjacent to V1? So we are given that first of all that if delta is the maximum degree of vertices in G. So capital delta is the maximum degree of vertices in G. So what are the maximum number of edges adjacent to V1? What do we mean by the degree of vertex? So if we want to so basically delta is the maximum degree of vertex. So we know that degree of V1 is less than equal to delta, right? Because delta is the maximum degree. So degree of V1 is less than equal to delta. If degree of V1 is less than equal to delta, so what are the maximum number of edges adjacent to V1? Won't it be less than maximum number of edges adjacent to maximum number of edges possible adjacent? Won't it be delta? That is, I'm saying maximum number of edges adjacent to V1 will be less than equal to delta. Is that clear why? So, see, number of edges adjacent to V1 is equal to the degree of vertex. So we see that number of edges adjacent to V1 is less than equal to delta. And similarly, edges, number of edges adjacent to V1 Vk will be less than equal to k delta. So is this clear? Is this this clear till this step, that total number of edges which are total number of edges which are adjacent to either V1, V2 or Vk will be less than equal to k delta. Is this clear?
Why that K is coming, ma'am?
Oh, so k is coming because we have k vertices, right? So
Curvatic. Okay, ma'am. Okay, it is.
V1 is adjacent to at most delta vertices. V1 and V2 will be adjacent to at least 2 delta. And
Okay, ma'am.
similarly,
Okay, ma'am. K
k
times of
times delta.
the delta. Okay,
Yes.
okay, okay.
So number of edges adjacent to V1. Now we have additional extra condition also, that this V1 to Vk is also a minimum, it is also a vertex cover, or it is also a minimum vertex cover. So is there, so can you tell, so is there any relation between total edges and number of edges adjacent to V1, number of edges adjacent to V1 Vk and total edges of G? Is there any relation between these two set? So first is our graph G. First we are saying that total edges, that is all the possible edges in the graph G, and this second set is the all the edges which are, all these edges which are adjacent to either V1, V2 or Vk. So is there any relation, and we are given that this V1 to Vk is a vertex cover. So is there any relation between these two sets? Like, will it be one? So won't the total edges will be equal to number of edges adjacent to V1 Vk? Because any edge in G, since Q is a vertex cover, any edge in G will be either will have at least one end point, which is V1, V2 or Vk. So all the edges are adjacent to at least one of these V1 or Vk. And we know that number of edges adjacent to V1 Vk is less than equal to k delta. And since total edges is equal to number of edges adjacent to this, we see that total number of edges are less than equal to k delta. So is this step clear, why total edges is less than equal to k delta?
Yes, ma'am.
And now if total edges is less than equal to k delta, from this we can see that k is greater than equal to total edges by delta, and k was the size of minimum vertex cover, which is equal to size of maximal matching by Koenig's theorem. So if we combine this and Koenig's theorem, we get that size of maximal matching is greater than equal to total edges by delta. And this was what we were required to show. So is this question clear?
Yes, ma'am. Clear, ma'am.
Is it clear to everybody? Can we move on?
Ma'am, that one doubt, ma'am.
Yes.
That del
Hmm.
Um, it is a maximum degree vertex in G or vertices in G, ma'am. Because we get the maximum degree at any one vertex, right?
No, no. Delta is basically maximum of all degrees.
Okay.
Maximum of degrees of vertex.
Okay, ma'am. Okay, ma'am.
Yeah. So this was like, so this delta is like, this delta is referred to the maximum degree, and this smaller delta is referred to minimum degree.
Minimum degree. Okay, ma'am. Okay.
So that delta only. So is this question clear?
Yes, ma'am.
Okay. Now, second question is this. G is a perfect matching. Oh, sorry. G has a perfect matching. Okay. Okay, before this question, I have to recall one theorem that we'll be using. So let's first recall that. So we have seen what is a vertex cover. Now, similar to vertex cover, we have an additional concept of edge cover. So what is so vertex cover? So this is what just an analogous definition. So vertex cover was a subset of vertices, and each edge should have at least one vertex adjacent to that set. Now edge cover. Now similarly we define the edge cover. So edge cover is the set of edges, and every vertex should adjacent to some edge. So that is the edge cover. So in this example, uh, yeah. So in this example, can you give a edge cover? So in this same example, can you give an edge cover? So basically you have to give a collection of edges such that such that every vertex is present in one of those edges. So like previously, since set of all vertices were always forming a vertex cover, so here also set of all edges will also form a edge cover. Now that is a trivial edge cover. Now we want to find a non-trivial one. That is a proper subset of set of edges which is covering all the vertices.
Take
So
all the matching edges,
yeah,
take all the matching edges,
take
and
and yes,
that non-matching edge from non-matching vertex.
yes, very good. So you are saying that take this set S equal to all the matching edges, which is A E B F D G, and now C and H are the only vertices which are left. So
Yeah.
take one edge from C F and one edge from D H D G.
Yes, ma'am.
Sorry, D H. So this will form a vertex cover. Very good. So sorry, this will form a edge cover. Edge
Let's
cover.
go.
So is it fine with everybody why this set is forming an edge cover?
Ma'am, can you
Yes.
repeat again? Edge cover.
Yes. So okay. So let me look at a cleaner page. Yes. So this was our graph, right? D. This was our graph. Pi. Sorry. Sorry, this is again. So, oh, okay, sorry. Just- Yes. So I was saying, what is an edge cover? edge cover is basically we are finding, so we have to find some set of edges which is covering all the vertices. So what did he suggest? He suggested that first we take all the, suppose I am taking this e prime now as a set, I take all these edges which are matched, say AE, BF and DG. So now if I'm taking these matched edges, what all vertices are they covering? So they are covering basically A, E, B, F, D and G. Now, but these three edges are not forming an edge cover because there are still two vertices C and H which are left, which are not covered by any of these edges. So but edge cover should have an edge which is covering all the vertices. So what we do now, we look at the leftover vertices and include one edge for each vertex. So this C was a leftover vertex, so we include this edge CF, and we also include this edge HD. Now if we look at these five edges, we see that all the vertices are covered. Therefore these five edges are forming an edge cover. Is it fine now?
Yes, ma'am. Thank you.
Yeah. Okay. Now we know what is an edge cover. The next thing is, what is an independent set? So we also defined it in the last week lecture. So what is an independent set? Independent set, by an independent set we mean a set. So we took a set of vertices in which there are, if we have a set of vertices, and those set of vertices should not have any edge between them. So that is an independent set, and this is a result that was proved in lecture, that if S is independent if and only if complement of S is a vertex cover. So now in this graph only, can you give me an independent set? Basically for independent set we are looking at some subset of vertices which have no possible edges between them. So in this graph, can we find some independent set? Examples of independent set in this graph.
Ma'am,
Yeah.
whether the independent set comprises of the vertices from particular partition or from X to Y.
There are no conditions on that. You can it can be anything. There are no conditions like.
Okay, ma'am. Okay.
Independent set is defined for a general graph. Like like in general graph also we can define an independent set. By independent, graph need not be bipartite. Basically we are just looking at a set of vertices which have no possible edges between them. But by definition bipartite graph will always have some non-trivial independent sets. So in this graph is bipartite. So you see this bipartitions are always independent, right? Because by definition,
Yes, ma'am. That's why I have asked that doubt,
yeah,
ma'am.
yeah. So A, B, C, D and E, F, G, H, they are independent set. Yes. Now if we, okay, so now basically this was a bipartite example. Suppose this is the graph now. A, B, sorry, let me write X, Y, Z, W, V. In this graph, can you give me an independent set? Okay, wait.
Ma'am, is it always bipartite only independent set or some other example also we can give?
Yes, yes. In this example only. So see, you see. Uh, so suppose if we take BC and G, BCG. This is also an independent set, right? So in bipartite graph also, it is not necessary that all the independent set will be a subset of some bipartition. So if you take this BCG here, this is also an independent set. And if a graph is not bipartite, then also if a graph is not bipartite, suppose this is that graph, and this graph, if this is a graph, this is a general graph. So does this have some independent set?
Can we say X, W and B,
XW and
D?
okay. So XW is correct, but we can't add V to it because see, we shouldn't have any edges. So WV is an edge. So this is not an independent set.
Okay.
But your thought was right. So XW is an independent set.
XW is an independent set. Okay.
Yeah. So this is just what is an independent set. And now the result is saying that if S is independent, complement of S will be a vertex cover. S will be independent if and only if complement of S is a vertex cover. This by definition is very trivial to prove. So this has been proved in class, but this is very trivial. So see, if S is independent, then we don't have any if S is independent, there are no possible edges between S. So any edge in graph G should have some vertex in S bar. Therefore we see that if S is independent, clearly S bar is a vertex cover. Is this fine? Why this implication is clear? Because if S is independent and we have to show that S bar is a vertex cover, we want to basically show that any edge S bar is vertex cover, we want to show that any edge should have at least one vertex in S bar. And since there are no possible edges between S, all the edges should have at least one vertex in S bar. Therefore, we see that if S is independent, the complement of S will be a vertex cover. So is this implication fine? Why is it happening?
Yes, ma'am.
Yes,
Yes.
ma'am. Yes, ma'am.
Yeah.
Yes. And similarly you can see the other way around. But now if we have this S is it, so now once we have this, so we get this result that size of maximal independent set and size of minimum vertex cover is equal to Vg. From this we can get this, because we have seen that suppose S is the maximal independent set, then S bar, we know that if S is independent, then S bar is a vertex cover. And we see that because S is the maximal independent set, S bar will be the minimum vertex cover. And order of S plus order of S bar is equal to the number of vertices. Therefore, we get this result that order of maximal independent set plus order of minimum vertex cover is equal to the total number of vertices. And then we have another result that size of minimum edge cover plus size of maximal matching is equal to order of vertices. So for time being, don't worry about the proof, but remember these two inequality. Remember these two equalities, that for a general graph G, size of maximum independent set and size of plus size of minimum vertex cover is equal to the order of vertices. And if we have a graph G with no isolated vertices, then size of minimum edge cover and size of maximum matching is the total number of vertices. So, remember, remembering these two equalities, let's solve the next question. So we have done. Yeah. Now we have given that. Yeah. So now we have given that G is a bipartite graph. And G also has a perfect matching. Then we have to find the size of maximum independent set in G. So first of all, what is a perfect matching? Perfect matching is basically matching which consists of all vertices of G. Okay. So now suppose we have this bipartite graph. Do you think this bipartite graph has a perfect matching? Okay. So perfect matching is basically a matching which is consisting of all the vertices of G. So if you are given this bipartite graph G, if this is the bipartite graph G, do you think this graph can have perfect matching? That is a matching which is consisting of all these vertices A, B, C, D, E, F, G. What do you think?
No, ma'am.
Why?
Here A, E, and C, F will be the taken in that matching. None other can be taken here, ma'am. So it does not covers all vertices.
Okay, this graph can't have a perfect matching. Yeah. Okay. Also, you see that here order, so this is X and this is Y. So if order of X is less than order of Y, what do you think? If order of X is less than order of Y, can this graph have a perfect matching? If
Not
we,
possible.
not possible, right?
Yes.
Is this clear to everybody that if a bipartite graph has a perfect matching, first, to prove this question, my claim 1 is that bipartite graph with perfect matching should have that order of X equals to order of Y. So is everyone convinced why this should happen? That if a if we have a bipartite graph in which one bipartition have less number of element, then that bipartite graph cannot have a perfect matching. In this case only you can see. So if order x is less than y, if order x is less than y, and since all the edges have one endpoint in x and one endpoint in y, so in any matching there will be some vertices. So if we have, so order x is less than y, so suppose x has k vertices v1 v2 v3 v4 vk, and y has more vertices than k. So w1 wk till wk and some more vertices. So see, if we want to if we are, and since in the bipartite in bipartite graph, one edge should be present, one vertex, each edge should have one vertex in x and one vertex in y. This graph cannot have a matching which have more edges than order of x, right? But order of y is greater than order of x. Therefore, in any matching, there will be some vertices of y which will be left over. Therefore, we see that if bipartite graph has a perfect matching, then both the bipartitions should have the same order. So is this fine?
Yes,
Yes,
ma'am.
ma'am, understood.
Intuitively, is it clear? Like this has also been proved in the lectures. You can look at the proof, but intuitively, is it clear to everyone why this should happen? We also gave a kind of a proof also. This is fine. So now we know that bipartite graph. So we want to find the signs of maximum independent set. So first we have shown that if a bipartite graph has perfect matching, then order of x is equal to order of y. Therefore, suppose order of x is equal to order of y is equal to n. Now if a bipartite graph has perfect matching, this is true. So now what do you think will be the size of matching? Size of maximal matching in graph?
N.
N. Size of maximal matching will be n. Now we want to find the size of maximum independent set. So if we know that size of maximum matching is n, can we find the size of maximum independent set? So here we'll be using two three equalities. First is that we have got that size of maximum matching in G is equal to n. Now, by Koenig's theorem, what is the size of maximum matching in bipartite graph equals to? What is it equal to?
Size of minimum
Size of minimum vertex cover,
vertex cover. Yes.
right? This is by Koenig's theorem. Koenig's theorem for bipartite graph. So this is not true in general for general graph. This is only true for bipartite graphs. Now size of minimum vertex cover. And did we have any relation between size of minimum vertex cover and size of maximum independent set? So what we had, that size of minimum vertex cover plus size of maximum independent set was equal to, from the last total number of vertices in G, right? And what are the total number of vertices in G? In our graph, in this case, if x is order of x is equal to order of y equal to n, what are the total number of vertices in G?
K plus 1.
uh what is k? uh so we so see,
2n.
hello,
N.
yeah. So we have got here that size of maximum matching in G is equal to n. So first we show that G has a perfect matching. G has perfect matching implies that order of x is equal to order of y, which is equal to n. And we also got that size of maximal matching was n. So, so now this is a bipartite graph on 2n vertices, right? Since order of x is n, order of y is n, total number of vertices in G is order x plus order y, which is 2n.
Yes, ma'am.
Yes.
Yes.
Yes. Now can we find, and we know that size of minimum vertex cover is n, and size of maximum independent set is equal to 2n. So we see that size of maximal independent set is equal to n, which is equal to total number of vertices divided by 2. So is this clear that, so now what we have got is that if G is a bipartite graph, conclusion that if G is a bipartite graph which has a perfect matching, then G has maximum independent set of size, total number of vertices divided by 2. So is this question clear to everybody? So I'll quickly recall the proof of this. So first, what was the question? We were given a bipartite graph with a perfect matching. Bipartite graph which has a perfect matching, and we wanted to calculate the size of maximum independent set. So now first we showed that if we have a bipartite graph with perfect matching, then both the bipartitions should have the same order, and we took that order to be, say, n. So was a bipartite graph with same order. Now since it has a perfect matching, that means size of matching, since it has perfect matching and it has 2n vertices, so we see that size of maximum matching was coming out to be n. And by Koenig's theorem, size of maximum matching is equal to size of minimum vertex cover. So we see that size of minimum vertex cover was also coming out to be n. And now we have another equality, that size of minimum vertex cover plus size of maximum independent set is equal to total number of vertices in G. Is equal to total number of vertices in G, and which total number of vertices in G were 2n. And if we put up all these values, we were able to see that the size of maximum independent set was coming out to be n, which was total number of vertices divided by 2. So is this question clear to everybody?
Yes, ma'am.
Okay. Now let's do another question. Okay, there's like, Okay, so this is the last question for today. So this is just recalling again the augmenting path thing. So first, so for so the this is your graph G, and you want to see if this graph G has an augmenting path with respect to M1 and M2. So now M1 is this A3 B3. So what do you think? Does it have an augmenting path with respect to M1? Okay, this is just recalling. So yeah, so augmenting this is the matching. A3 B3 is a matching. Now you want to see if G has an augmenting path with respect to this matching. Okay, this I'm saying that this
Yes,
does.
ma'am.
Yes, so what is the augmenting path? Yes, so we see we have, so these are the matched vertex. So augmenting path should start from a vertex which is unmatched. So if we take A2, we see that if we take A2 B1, this is an augmenting path. And similarly, I'm leaving as homework that this has an augmenting path, and you try to find it. Okay, so this was this was all the questions for today. So now if you have any doubt from today week's problem, or if you have any other question regarding these 4 week problems, you can ask. Or if you have any doubt in any of the questions which are solved today, then also you can ask.
Ma'am, that last question of assignment 1, graded assignment, ma'am.
Okay, yeah, okay, yeah. Okay, so okay, last question was, so question was, I think you have 99 people. Yeah, so can you like once do you have the question with you?
Yes, ma'am.
Okay, wait, let me check the question.
May I read it, ma'am?
uh yes, you can read it. There are
There are
99, huh, yeah.
99.
Hmm.
There are 99 members in a club,
Hmm.
and every member claims that he would play bridge only with someone he knows.
Okay, yeah.
Each member knows at least other 67 members.
Okay, so degree V is greater than equal to 67, right?
Yes, ma'am. Yes. Then there must be 4 members who can play bridge together.
Okay. So see, so we have 99 vertices basically, and we are saying that there is an edge if two people know each other, right?
Yes, ma'am.
People know each other. So now if we want to convert this into a graph theory problem, so we have that 99 vertices, and degree of each vertex is greater than equal to 67. Now we want to show that there are 4 vertices which are connected with each other, right?
Yes,
There
ma'am.
exists at least, there exists some 4 vertices which are connected to each other. Okay, so now if we want to do this, see, so we have 99 people. So we have 99 vertices. Suppose we pick V1. Since degree of V1 is greater than equal to 67. So V1 is not attached to at most. So we have V1, and suppose degree V1 is greater than equal to 67. So suppose it has 67 members. So 67, 68, 99. So 99 minus 68 is 31. So first of all, you observe that since degree of each vertex is greater than equal to 67, each vertex is not attached to at most 31 vertices. Is this clear? So for each vertex, there are at most 31 there can be maximum 31 vertices which are not attached, right? So now if we want to show that there are 4 vertices which are connected, now we want to show that there are 4 vertices which are connected to each other. So suppose pick V1. Now choose V2 to be some neighbor of V1. Okay. So now we have V1 here and V2 here. Now we know that V1 is not attached to at most 31 members. And similarly, V2 is also not attached to at most 31 members. So these are the maximum possibilities. So we know, so V1, V2 will have at least one common neighbor. So V1 is not attached to at most 31 members, say W1, W31, and similarly V2 is not attached to say U1, U31. So if we look at the total 99 vertices, if we remove this V1, V2, and if we remove these 62 vertices, so total vertices minus V1 minus V2 minus these 62 vertices which are the maximum possible one. So we see that 99 minus 64 is still greater than 0. So we can choose a V3. So we see that we can pick V3 from the remaining one. Now we do the same thing for this. Now V1 is not attached. V1, V2, V3 are connected to each other. V1 is not attached to 31 members, at most 31 members. V2 is also not attached to at most 31 members, and V3 is also not attached to at most 31 members. So if we add these up, we see that V1, V2, V3 together at maximum cannot be attached to 93 members, and these and V1, V2, V3 are other three people. So other than these 96 people, we can choose another V4. So we see that if we other than these we can choose another V4, and we'll see that they will be connected to each other. So we are able to choose 4 vertices. Is it clear?
Yes, ma'am. Ma'am, but that 99 minus 68, why are you subtracting that 68 from that 99, ma'am? 68.
99, 62, sorry.
Okay,
64,
ma'am.
64, because 64, yeah. So see, so I am saying that V1 is not attached to at most 31 people, and V2 is also not attached to at most 31 people. So these are 31 here, these are 31 here, and V1, V2, add these two also. So 31, 31, 62, V1, 6. So all these are 64. We are picking some vertex other than these 64 vertex.
Okay, ma'am. Okay, ma'am.
And
Ma'am,
now when we have v3, so we pick v3 then. Now v3 is also not attached to at most 31. So now we have 31 plus 31 plus 31, which is 93. And then we have v1, v2, v3, which is 3 more, 96. So now we pick some vertex other than these 96 vertex. And we'll see that they will be connected to each other
yes, ma'am.
by our
Yes, ma'am.
choice.
Ma'am, I have asked about that initial subtraction, ma'am. V1 is not attached to at most 31 vertices.
Yes.
Why you are subtracting that 68, ma'am? Particularly 68.
Because yes, oh, why we are subtracting 68? Because see, degree so v1 is there, degree v1 is greater than equal to 67. So
Yes.
v1 is attached to at least 67 vertices. So we have at least 67 vertices. We know that at least 67 vertices are there through which v1 is attached. So if so, the maximum number of vertices through which v1 is not attached are vertices which are other than these vertices. So these are
Okay, ma'am.
67
Okay.
and this is 1.
Okay, ma'am. Clear, ma'am. Clear.
Okay. Yeah. Okay. Any other question?
Thank you, ma'am.
Can you
Okay.
suggest me a reference book, ma'am?
Reference book for this course. So in the in the lectures, sir has mentioned 2 books, right?
Ah, yes.
Yeah.
Both books are reference book.
Yes. Yeah.
Okay, thank you.
Any other questions? Okay, then I'll end the session.
Ma'am, one more question, ma'am.
Yes, okay, yeah.
In fourth assignment, ma'am, graded assignment, I have a doubt in that question, ma'am. Is there a cubic graph without a one factor?
Wait. So fourth week, yeah. The graded one, yes, yeah,
Yes, ma'am. Second question, ma'am.
yes,
Assignment 4, second question.
yes,
Is there a cubic graph without a one factor?
yes, yeah. So see, so okay, I'll present it. So uh, this is this is true, right? So in the solution there is an example of a graph, cubic graph, which has no one factor. uh, Wait. Present. Okay. Yes, so see, uh yeah, so this is a cubic graph, but it does not have a one factor. So this,
Ma'am,
yeah, so this
the,
will be shown. So in the next lecture you'll see in the next lecture 5, there is a generalized version of Hall's theorem, right?
okay, ma'am.
In the lecture 5 there will be a
Uh,
generalized version of Hall's theorem. From that you will be able to show that this won't have a matching.
okay, ma'am. I want to know about what is that one factor means, ma'am. Actually, what it means, one
Ma-
factor.
One factor is just matching. By one factor we mean matching. Oh,
Okay,
one
ma'am.
factor is regular one graph. Regular
Oh,
one
okay, ma'am.
graph,
Okay, ma'am.
which is covering all the vertices. So in a sense, you are asking for a perfect matching.
Okay, ma'am. Okay, ma'am.
One factor is a perfect matching.
Thank you, ma'am. Thank you.
Okay. Okay, then I'll end the call.